Cosmic strings are hypothetical one-dimensional defects in spacetime that may have formed in the early universe. They are not strings in the everyday sense, but extremely thin, immensely dense structures stretching across astronomical distances. If they exist, cosmic strings would represent relics of high-energy processes that occurred fractions of a second after the Big Bang. Their discovery would provide direct evidence about fundamental forces and conditions at energies far beyond those accessible in modern particle accelerators. The concept of cosmic strings originates from field theory and symmetry breaking. In the early universe, temperatures were extraordinarily high, and fundamental forces may have been unified into a single interaction. As the universe expanded and cooled, this unified symmetry broke into the distinct forces we observe today, such as electromagnetism and the weak and strong nuclear forces. During these phase transitions, defects could have formed in the fabric of fields permeating space, similar to cracks that appear when water freezes into ice. These defects arise because different regions of space may settle into different vacuum states as symmetry breaks. If the transition occurs randomly across causally disconnected regions, mismatches can occur where domains meet. In some models, these mismatches produce line-like defects known as cosmic strings. Unlike ordinary matter, which consists of particles with finite volume, cosmic strings would be effectively one-dimensional, with enormous energy concentrated along their length. The thickness of a cosmic string would be extremely small, potentially far smaller than a proton, yet its mass per unit length would be enormous. A string only a few kilometers long could outweigh entire mountain ranges. This immense energy density would strongly curve space-time around it. However, unlike black holes, cosmic strings would not have event horizons. Instead, they would create a distinctive gravitational effect by producing a conical distortion in spacetime. One observable consequence of a cosmic string would be gravitational lensing. Because of the spacetime distortion, light passing on either side of a string would be deflected. Unlike lensing by massive objects like galaxies, which produces arcs and rings, lensing by a cosmic string would create double images of background objects without distortion. Detecting such characteristic lensing patterns would provide evidence for their existence. So far, no confirmed observations have revealed such signatures. Cosmic strings may also generate gravitational waves. If strings form loops due to intersections or oscillations, these loops would emit gravitational radiation as they evolve. Networks of cosmic strings could produce a stochastic gravitational wave background. Modern detectors, such as pulsar timing arrays and laser interferometers, search for such signals. Recent hints of low-frequency gravitational wave backgrounds have led some researchers to reconsider cosmic string models as possible explanations, although no definitive link has been established. Another potential signature involves the cosmic microwave background radiation. Cosmic strings could leave subtle imprints on temperature anisotropies by inducing discontinuities along their paths. Precise measurements from satellites like Planck have placed strong constraints on the allowed abundance and tension of cosmic strings. Current data suggest that if cosmic strings exist, their contribution to cosmic structure must be limited. It is important to distinguish cosmic strings from strings in string theory. While the names are similar, they arise from different contexts. Cosmic strings are topological defects predicted by certain grand unified field theories. In contrast, fundamental strings in string theory are microscopic objects that constitute the basic building blocks of particles. However, some versions of string theory predict cosmic superstrings, which share properties with field-theoretic cosmic strings and might be stretched to cosmological scales during inflation. The existence of cosmic strings would have profound implications. They would serve as fossils of early universe physics, revealing information about energy scales trillions of times higher than those probed in laboratories. They might also influence galaxy formation by acting as seeds for matter clustering, although current models indicate that inflation-generated density fluctuations dominate structure formation. Despite their theoretical appeal, cosmic strings remain speculative. Extensive observational efforts have yet to find conclusive evidence. As experimental sensitivity improves, particularly in gravitational wave astronomy, the parameter space for cosmic strings continues to shrink. Either future detections will reveal their presence, or constraints will rule out many models that predict them. In conclusion, Cosmic strings are hypothetical, one-dimensional defects formed during symmetry-breaking phase transitions in the early universe. Infinitely thin yet immensely dense, they would warp spacetime and produce distinctive gravitational effects. Although no confirmed observations exist, ongoing searches through gravitational lensing, cosmic microwave background analysis, and gravitational wave detection continue to test their existence. Whether they are relics of primordial physics or mathematical artifacts, cosmic strings represent a compelling intersection of cosmology, particle physics, and the quest to understand the universe at its most fundamental level. If you like the video, share it and don't forget to subscribe. Cosmic Secrets 108, turn on notifications. See you in the next video.